Welcome to AP Pre-Calculus. Today we're going to look at 1.9, rational functions and vertical asymptotes. In this daily video number 1, we're going to investigate how to determine the vertical asymptotes of rational functions. So I'm very happy to be with you today. My name is Carolyn Williamson, and I'm in Aylett, Virginia, and we will be looking at some pre-calculus by first warming up. So we want to find the real zeros of these following rational functions. That skill is going to help us in this particular lesson. So by factoring the numerator and denominator, you can look at the real zeros coming from factors in the numerator that are in the domain, give answers in the domain of your function. In other words, you're not going to cause division by 0, and that would be 0 and -2. For the second example, factor this as well, and you'll see that because you do have x plus 2 in both the numerator and the denominator, our only real zero is going to be 3, since -2 is not in the domain of this function. So remember, the real zeros of rational functions correspond only to real zeros of the numerator for the values that are in the domain of the function. Today, we're going to look at these vertical asymptotes of a rational function. In learning objective 1.8a, we examined real zeros of a rational function, and in doing so, we basically used the numerator as our primary focus. Now we're going to look at how the real zeros in the denominator of a rational function can aid in determining its vertical asymptotes. And then we're going to look at the unbounded behavior around the vertical asymptotes of a rational function. So let's look at an example. So for vertical asymptotes of a rational function, we first want to take a look at this and notice that once we factor this, we'll have a whole at x equals 5. It has an equal multiplicity of 1 in both the numerator and the denominator, and so that indicates we have a whole there. So that was not going to give us a vertical asymptote. Notice I said multiplicity of 1 in both the numerator and denominator. If that's not the case, we might have a different situation, which we'll see in a later example. So we do end up having a reduced form of x plus 7 over x plus 2. That tells us that we're going to have real zeros in both the numerator and denominator of 5 and -7. So what does that give us as far as vertical asymptotes go? Well, you take a look at the reduced form and you will see that you would have division by 0 if x equals -2, and that is where you'll have a vertical asymptote. Notice that the factor that canceled x minus 5 does give us a whole there. So our unique real zero of the denominator is -2, and the graph of the function has a vertical asymptote there. In example 2, let's take a look at this particular problem. And notice I mentioned multiplicity of 1 in the previous one. Well, we'll take a look at this one. When we factor this, we see that we have x plus 1 factor, multiplicity of 1 in the numerator, but multiplicity of 2 in the denominator. So that does not reduce completely. Once we reduce x plus 1, we're still left with an x plus 1 in our denominator. Because of that multiplicity of 2, that will not be a whole. That is going to be a vertical asymptote. So our real zeros of the numerator were -1 and -2. The denominator, 0, -1, with a multiplicity of 2. So that tells us we will have a vertical asymptote, certainly at 0, and we will also have a vertical asymptote at -1 because the multiplicity of that 0, -1 in the denominator is larger. So that factor is not reduced completely away. It's not going to be a whole. It's going to be a vertical asymptote there as well. So pay attention to the multiplicity when you're finding vertical asymptotes. So we will have 2 here at 0, which is the y-axis, and at x equals -1 are shown on this graph. In example 3, we're going to go back and look at this first problem, and we're going to talk a little bit about how we know what's happening as we approach -2 from the right and from the left. And so when you see that little sign there, that little negative, if you think about the direction on the number line, when it goes negative direction, it's going to the left. So when you see that, that means you're looking at -2 from the left, from the negative side. And the positive means you're looking at -2 from the positive side. So if you notice how you're getting closer and closer to this asymptote as you get closer and closer to -2, our graph is just shooting downwards. So we say that this function here has the vertical asymptote, and this behavior as it gets closer and closer to the vertical asymptote is going to -infinity from the left. Then from the right, you're going up, up, up. So we say that the end behavior here, as we are getting closer and closer to this vertical asymptote, as we approach 2 from the positive side, is going to positive infinity. So we can use this limiting behavior, looking at 2 from either side, using this notation, and we can describe where the graph is going by using either positive or negative infinity. So let's practice. So we have this example, and we're going to want to take a look at what's happening around -3, because you'll notice you have a hole here at -8 that's not quite on our graph, so you don't see a hole there. It ends before it gets there, but you are left with a vertical asymptote at -3. And so when you look at the behavior of this graph, as you approach -3 from the left, we see that this is going to -infinity. And as you approach -3 from the right, you can see that it's going to positive infinity. It doesn't always work that way, but it has in the last couple of examples that we did look at. So what should we take away? Finding vertical asymptotes of a rational function requires examining these real zeros unique to the denominator, and those with multiplicity in the denominator greater than that in the numerator. Those are where you're going to be getting those vertical asymptotes. The behavior of the output values of a rational function near a vertical asymptote will either increase, meaning go to positive infinity, or decrease, meaning going to negative infinity without bound, as you get closer to that vertical asymptote from either side. Thank you for joining us today, and have a good day.